All right. Okay, so yeah, I've got 8:35. I'm going to get started. This is COMP2804 Discrete Structures 2, and I'm Daryl Hill, the instructor. So we're here on Friday, March 10th. We're going to finish talking about independent events. And incidentally, this is, of course, the last lecture for you to be able to do assignment 3. Now, you should have actually probably been able to do assignment 3 before now, but this might give you a couple of extra tools. And this is the last lecture that's going to be on the next test. So yeah, everything from pigeonhole principle till now will be on the test 2. Other than that, it's a pretty slow week, I guess, but any questions before we continue? Okay, so we're going to continue to talk about independent events. So last class, why did I move that down? I don't remember. Last class, we were talking about independent events, and we talked a lot about what is an independent event, what makes two events independent, and how can we verify that they're independent, and the different types of independence, so pairwise versus mutual, and things like that. This class, we're going to, as I mentioned, some of the questions that we ask you is, are two events independent? And that's a perfectly fair question, but also we will ask you questions where we just tell you that you have a set of mutually independent events, and then when you know that, you can use these extra tools in order to simplify your calculations. So that's what we're going to do today. So what happens sometimes, I mean, we've talked about sample spaces and event spaces, right? So these are just sets and subsets. When we talk about independent events, sometimes we use different notation because it's sort of easier. So hopefully this will become more clear as we go through the lecture. But for now, let's just highlight some of the things that we will be doing, which is we will be substituting some logic operators for set operations. And so I'll explain a little bit how that works. These are basically equivalent. And when I say, if we use something like this, it doesn't mean you can't use this, but we're conveying something a little bit different when we do this. All of the tools we used up till now will still work on independent events, but because if we know if we know events are mutually independent, then we get a few more tools. That's basically all. Okay, so we describe events in English, and we can describe events as sets, but we can also describe sets using logical predicates. So let's say I have these 4 sets. So A is everyone with black hair, and my sample space is all people, or this would be my universe, I guess, in this sense. So A is everyone with black hair, B is everyone with brown eyes, C is everyone with black hair or brown eyes, and D is everyone with black hair and brown eyes. So these are all sets, and I can express them as such. So C is the union, right, because I used or here, of A and B. So it's everyone with black hair or with brown eyes. But I can also write this using the set builder notation. So C is the set consisting of these elements X, such that X has black hair, and then or X has brown eyes, right? And these X, it's not written explicitly here, but this is taken from the, in our examples, it'll be taken from the sample space, but you can think of it, when you learned it in 1805, we talked about the universe, right? So the universe is just everything that you were considering with these sets. So this V here is the logical OR operator, and it's basically a predicate, right? Yeah. And if I take D, I can express D as A intersect B, that is everyone who has black hair and brown eyes. Or I can write it using my set builder notation again. So it's all elements X such that X has black hair and X has brown eyes, right? So this is the logical AND. All right, so, these are Boolean operators, and in some sense, this, I take an element, I plug it in, and this returns either true or false. X either has black hair or does not have black hair. X has brown eyes or does not have brown eyes, and then I just take the conjunction of those. Okay. We can also, we'll define a few more sets here. People who do not have black hair, people with blonde hair, and people with black hair. So A is equal to, if I look at the set operation, A is equal to the complement of C, right? So C is the people with black hair, and then so the people who do not have black hair is the complement. So I can define these using set operations, or I can say that, again, this is from 1805. These are predicates, right? So essentially I take some element X from my universe, I plug it into this predicate, people who do not have black hair, and if it returns true or false, basically. And in some sense, if it returns true, then X would be in this set. And I can say that, well, since these both return true or false, I can use the negation here. So I can say that if it returns true here, then it's going to return false here and vice versa, right? So this is the negation symbol, and it just flips it from true to false or from false to true. So these are equivalent in this sense. And finally, the implies, right? So B of X implies A of X, which means that if I say someone has blonde hair, then that implies that they do not have black hair, right? Which is true. In terms of set operations, this is equivalent to B being a subset of A, right? So I have all of the people that do not have black hair, and then the blonde people are a subset of that. They're not all of it, because I could have brown hair outside of that, or whatever, maybe blue or green or whatever. But yeah, so if B is a subset of A, then being a part of this set implies that I'm also a part of this larger set. Okay, so that's basically how we map these English and logic and set operations together. All right, so any questions so far? All right, so we'll see why we're doing that in a second. But yeah, so let's look at a quick example. Let's consider flipping a coin and rolling a fair six-sided die. So we will look at this the old way, right, with just set operations, and then we will look at how we can replace those set operations with these Boolean operations. So the sample space is a bunch of ordered pairs where the first element is heads or tails, and the second element is a value 1 through 6. Right, so these are all possibilities. I flip heads, and then I roll some value between 1 and 6, or I flip tails, and then I roll some value between 1 and 6. Yeah, so that's my sample space, and I can define events, A, that the coin comes up heads, and B, that the result of the die is even. Okay, so it's a fair coin and a fair six-sided die, and which sort of goes without saying that these are mutually independent events, right? So the flip of my coin does not impact the outcome of my die. Not only does it not affect the probability, it doesn't affect the outcome at all. So these are sort of, in some sense, obviously mutually independent. And we can take advantage of that when we're computing things. So first we can compute things the old-fashioned way. So if I wanted the probability of event A, what's the probability that event comes up heads? Well, I can look at all of the outcomes from my sample space that have heads, and there's 6 of them. And I can put the size of A over the size of the sample space. And the same for B. If I wanted to, look at this set B, the result of the die is even. Well, I'm looking at all of the outcomes where the die roll is even, and I don't really care about whether it's heads or tails. All right, so I can, if I want to look at the intersection of A and B, I can write it like this, or I can write it like this. This is a set operation, and I would, A intersect B is all of the elements that I have in common between A and B. And then I can use the fact that this is a uniform probability space to say that, well, probability of A intersect B is the size of A intersect B over the size of the sample space. 3/12, which is 1/4. However, I can also, I think I did this a little out of order. All right, so yeah, I can also determine A union B, again, as simple set operations. I take everything that's in A and everything that's in B, and I combine them together, right? Throw away the duplicates. A union B has 9 elements, so the probability of A union B is 9/12, which is 3/4. We know how to do that. However, right, so A, the event that the coin comes up heads, well, the coin is independent of the die roll, right? So we're doing a lot of extra work here seemingly for nothing, right? I can determine the probability that the coin comes up heads without actually looking at the entire sample space. It's not wrong to do that. This still works, right? This gives us the right answer, but it's extra work. So what I can do instead, I can take advantage of the fact that the die and the die and the coin are fair and independent. This only depends on the flip of the coin, and this only depends on the roll of the die. So I'm just going to look at them in their own little sample spaces, right? So the flip of the coin has a sample space of heads or tails, and A in this case is simply heads. And if I look at the roll of the die, well, that is 1, 2, up to 6. And then B, the result of the die is even, is simply 2, 4, or 6. Right? So I don't have to count these entire sample spaces. I can just take little mini sample spaces because these are independent events. So then the probability of A intersect B becomes the probability of A and B. And then we can use what we know is that if they're independent, then that probability is equal to the product of the individual probabilities. The probability of A is, of course, 1/2. Probability that I flip a coin, it comes up heads. The probability of B is 3/6, which is just, 3 possible. All the even rolls are 3 of them out of 6 possible. So that is 1/2 times 1/2, which is equal to 1/4. Okay, so that's, when we are taking that sort of shortcut, then the convention is to use these logical operators instead, right? Because we're doing a lot of extra work here. We're still going to get the right answer, but we can look at this event as being independent of this event, and then it makes our computations easier in some sense. Okay, yeah, so event A, we only need to consider the sample space of the coin, and event B, only the sample space of the die. So we can kind of separate our 2 events. Okay, questions so far? All right. And this is basically when you start learning probability in high school, although high school was many years ago for me. This is typically where you start, because actually this is the easy stuff, right? Independent events, how many ways can I roll 2 dice and things like that. These are easy. So we started with the hard stuff, and then we came back to the easy stuff, but we want to be able to understand the easy stuff through this lens, right? So we have a more complete framework now, because independent events are not just die rolls and coin flips, they're also other events that maybe don't seem independent, but they actually are. Okay. If I want to take the A union B, well, and sort of convert that to this, take advantage of independence, well, that's not quite so easy, right? I can't really do this because, well, I have no way to, these are not, you might be tempted to use the sum rule, but of course, these are not disjoint, right? So disjoint and independent are 2 different things. These 2 events are not disjoint because they have elements in common, right? H2, H2, H4, H4, H6, and H6. So they're not disjoint, so I can't use the sum rule. So independence gives us this, that I can, if I take the intersection, I get the product, but it does not really solve our union problem. So we have to be a little clever about that. Okay, so let's take a look at another simple example. So we're going to take a value n, that's at least 2, and assume we flip n coins. These coins are fair and independent. And we will define an event AI is that the ith coin comes up heads. Right, so what we would do before is we would make an n tuple, right? Find our sample space. There's n possible coin flips. Each one has 2 outcomes. So I would, say, well, there's 2 ways to choose that, 2 ways to choose that. And then I would look at the subset that corresponds to this event. And you can do that, and it will work. But since these are all fair and independent coins, I can just treat them as independent events and just use their individual probabilities. Okay, so each flip is mutually independent. So all of these flips are, yeah. So consider the event. A is that all of my n coin flips come up heads. Okay, so what is the probability of this? Well, since they're independent and we're using the logical AND, which is the intersection, we can write our probability of event A is that all coins come up heads as the probability of the intersection of all these events. We use our independence, and now it becomes the product of the individual probabilities. So then what's the probability that all n coins come up heads? Yeah. Sorry? Yeah. Oh, okay, yeah. So you mean like any individual, yes, all right. Yes, so it is the probability of any one of these to the nth power, right? Since they all have the same probability, and that probability is 1/2. So 1/2 to the power n, which you could also write like this, right? So technically this is equal to that, 1 to the n over 2 to the n, and 1 to the n is simply 1. So those are all equivalent. Okay, so that's independence. And again, most of the time when you start learning probability, this is where you start. We came here after a long detour. All right, so let's look at another example. Let's say we have a circuit C, and that's why I moved that before. All right, well, there are n components in my circuit, and so these are numbered C or labeled C1, C2 up to Cn. And then we will define an event AI is the event that that component fails. Right, so when you have to do, if you make a circuit board, you have to do this quality assurance. So you test these things, and then some of them break. Right, this is completely normal. If too many of them break, then of course you have to look at your procedures. You have to clean up or tighten up some of the machines or whatever. But yeah, so I'm making these circuits. These circuits are made of components, and I want to determine what's the likelihood of these components failing. Well, let's say that we have some value, I don't know what it is, but some value P, right? P is just a probability. So it's some value between 0 and 1. Okay, so any individual component fails with probability P and mutually independent of all the other components, right? So that's maybe not, well, that's pretty true, I guess, in general. So we'll look at a couple scenarios. So I'll say that my circuit C fails if at least one component fails, right? So the only way my circuit C is good is if none of the components fail. If one or more fail, then C fails. Okay. So let's find the probability of that. So we'll call the event that the circuit fails, we'll call that event A. And the probability of A, well, what's the probability of A? We're going to write it in terms, we're using our mutual independence. We're using our mutual independence. So we're going to write A in terms of these using our logical operators. So I have, well, this circuit fails if component 1 fails, or if component 2 fails, or if component 3 fails, or if component n fails, and any combination of failing, then our circuit fails. Okay, does that make sense? Questions so far? All right, so this is a trouble spot for us. We can't exactly use our independence. So this corresponds to union. And as mentioned, at this point, you might be tempted to use the sum rule. But again, if you go back to the underlying sample space, these are not disjoint, right? I could have outcomes where both of these circuits fail. And then some other circuits might fail or might not, but I have a bunch of outcomes. So these are not disjoint. These are, they're all overlapping in some sense. So we can't use the sum rule. We could start using inclusion, exclusion, and counting them. We could do that, but there are potentially a lot of terms to that equation. Okay, so of course, we want to somehow get back to our logical and our intersection, so we could use the fact that they're independent, right? So if we wanted to know this probability, for instance, we could find it, right? We know this probability because these are independent. But the fact that these are independent also gives us something else. It gives us the fact that, this is independent of this. This is independent of this, and so on. So we can maybe use the complements in order to find something that we can compute, right? And so to get the complement here, this is going back to De Morgan's law. Okay, so we want to find this probability, and we're going to use the complement rule. So the probability that our circuit fails is 1 minus the probability that, the circuit does not fail. The circuit does not fail. Well, we can define that as, well, this is the complement of A or the negation of A. We're mixing and matching here some set operations with some logical operations. But yeah, so they're all sort of the same under the hood, but so yeah, the complement of A is equal to the complement of all of these. And if I apply De Morgan's law, then I get, right, so the complement of the union, or in this case, the logical OR, is the intersection of the individual complements, or the conjunction of the negations. Okay, does that, everybody remember De Morgan's law? So yeah, we'll be using that quite a bit to solve these types of problems. And of course, we have that all of these are independent with each other, right? So if we want to determine the probability of A complement, it's the probability of this, which is the product of the individual probabilities. Okay, so now what are those individual probabilities? Well, we'll just use the complement rule again. So the probability that circuit I does not fail is 1 minus the probability that circuit I does fail. Okay, so the probability that circuit I does fail is P, right? We define that up here. So then the probability that circuit I does not fail is 1 minus P. And then, well, we can write out our expression. Each of these is equal to 1 minus P. So it's the product of 1 minus P times itself n times, or 1 minus P to the power n. Okay, questions so far? Okay, good. Okay, so now I still have not, this is my probability of that the circuit does not fail. So the probability that the circuit does fail is 1 minus this probability, which is 1 minus P to the power n. And there are ways to simplify this using approximations, but this is good enough for now. But we can, if we think about it a little more, let's look at how this behaves as n gets larger and larger. So as n goes to infinity, well, let's start with something simple or more simple. The limit as n goes to infinity of 1 minus p to the power n. Well, we know that p is between 0 and 1. And so we know that 1 minus p is also between 0 and 1. All right, so what's the limit as n goes to infinity? So limits, right? So if I could take any fraction. Because it's less than 1, every time I multiply it by itself, it gets smaller and smaller, right? Because it's between 0 and 1. Let's say it was a half. So half times itself is a quarter, times itself again is an eighth, times itself again is a 1/16, times itself infinite number of times is 1 over infinity, which is 0, right? So the limit of this expression as n goes to infinity is 0. And that's not, of course, we can never reach infinity, but this tells us that if my circuit depends, well, okay, let's go back to our original expression first. So the limit as n goes to infinity of 1 minus p to the power n, well, this part goes to 0. So then I get 1 minus 0 or 1. What that means is that as my circuit gets bigger and bigger, if every component must work, then as n goes to infinity, it's going to break or fail with probability 1. Right? So it pays to have smaller sized circuits made of less components because they're more reliable. All right, questions? Okay. We can also look at this. So C fails when all components fail. So my circuit fails if every single component fails. Again, we will define the event A is that C fails. So this happens if and only if circuit 1 fails and circuit 2 fails and all of the circuits fail. So here we're actually already in good shape. This is the intersection of all of these events. And these are independent events, so they are equal to the product of all of the individual probabilities. Each of these has probability P of failing. So we just get, P times itself n times, or P to the power n. So if my circuit only fails, if every single component only fails, well, as n grows to infinity in this case, again, since P is between 0 and 1, the limit as n goes to infinity is going to be 0. It just gets smaller and smaller every time I multiply it by itself. Okay, how are we doing? All right, questions so far? Okay, let's look at, yeah, sure, we'll ask ourselves a couple more questions in this vein. I don't think we will go over every single example of this. You're free to look at it or come to office hours and I'll explain it to you. But let's think about what is the probability that exactly K circuits fail, right? So we have N circuits and we have K of them failing. So this is my event that all circuits fail, but now I want that some of them fail and some of them don't. All right, so this is going to be that, well, maybe A1 fails, but A2 does not fail. A3 fails, but A4 does not, etc. Okay, so this, I think, should be pretty clear. If I'm looking for what is the probability that exactly K circuits fail, I'm looking at the intersection of K circuits failing with N minus K of them not failing. So then Yeah, I know that the probability of AI is P and the probability of not AI is 1 minus P. All right, well, let's start with something simpler than that. Let's start with 5 circuits, C1 through C5, and we'll look at the probability that exactly 2 fail and that we know which 2 are failing, C2 and C5, and that the rest of them do not fail. Okay, so the probability that circuit 2 and 5 fail is equal to the probability of these events, right? So here is circuit 1 does not fail, circuit 2 does fail, circuit 3 does not, circuit 4 does not, and 5 does. Well, that's pretty straightforward. These are all independent, so I can compute the probabilities. I substitute P in for a circuit failing and 1 minus P for when the circuit does not. And I get 3 of these terms, 1 minus P and 2 of the P's. So that's P squared times 1 minus P cubed, right? So multiplication is commutative. I could just move these terms around and collect them. All right, so that's out of 5 circuits that I know exactly C2 and C5 fail. But if I want to find the probability that exactly 2 circuits fail, maybe it's not C2 and C5. All right, it could be C1 and C2, or C1 and C5, or C2 and C3. In fact, I have to look at every combination of 2 circuits failing. So how many combinations are there? So how many ways? Yeah. Yeah, so there's 5, choose 2 of these. So this is the probability that exactly, exactly C2 and C5 fail and the rest don't fail, but I have to look at all possible combinations of 2 circuits failing. So I can multiply by 5, choose 2. And why am I multiplying? Well, if I step back a little bit and think about it, each of these corresponds to an outcome, right? Going back to my sample space and all of that stuff. And I'm looking at, so each of them corresponds to an outcome, and I have 5, choose 2 of these outcomes where exactly 2 circuits fail. So I'm just summing them up, right? So, right, my event, the probability of A is equal to the sum of the individual probabilities, right, of each outcome in that event. So yeah, I'm sort of, again, I'm mixing and matching the paradigms, but they're not different. We're expressing them a little differently, but all our old rules still apply. We're just taking some shortcuts. So 5, choose 2 times that. Starts to look a little like Newton, but yeah. Questions? Okay. So in general, for n, I can write it as n choose k, p to the k, 1 minus p to the n minus k. All right, and we won't take this right now because there's a lot of heavy math coming up still, and I don't want to break you down just yet. But if I summed over every possible value k from 0 to n, then I have Newton's binomial theorem, right? And so if I did that, this would all sum to 1. All right, which we could show, but I think I'm going to skip that and we'll go to the next example. But yeah, any questions? All right. So yeah, we'll come back to that later, possibly, or I'll explain it if you come to office hours. Okay, so something more exciting, ninjas and fire. I was really bored when I made these slides, I think. But yeah, you guys know what linked list is? I'll briefly explain it, but is there anybody not sort of at least somewhat familiar with a linked list? Okay, so a linked list is a data structure. So in each of these, I have nodes in my linked list, and each of them might store a value, right? So I call this node U, but really this might store anything. This could store a name, perhaps, Bob, and this is Al, or whatever. I'm just storing things in my linked list the same as I would any other list. And this is a singly linked list, which means that I start with a pointer to the head. So initially I can only see what's in the first node of my list. So maybe there's A here. So I can see that. If I want to see what's in another part of my node, I have to use this successor, or sorry, another part of my list, I have to use this successor function, right? So I go from, let's call this, well, let's call this 1. So I'll say, I'm at the head, I call this successor to 1, and this gives me back 2, which is a pointer to the second node. Okay, so if I wanted to see what's in the third node, I would have to call successor 1, and then I would have to call successor from here, and this would bring me to the third node. All that to say is that if I want to see what's at, location 4 in my linked list, I start at 1, I move to 2, I move to 3, then I move to 4, and then I can grab what's at 4. And I can't walk backwards, I can only walk forwards. What I can do though is go back to the head and start over. So I can only walk through one direction, and I can walk through to the end. I can never back up, but I can always start back over in this scenario. Okay, so in this linked list, what we want to do is we want to return, so this is what I just explained. We want to return one of these elements uniformly at random. Okay, so this is actually, this algorithm in particular, I don't know if it gets used itself, but versions of it do get used, and I'll explain sort of the context. But so I want to choose a uniformly random node from this list. So what that means is, in this case, my linked list has 5 nodes. So when you ask for a random node, I'm going to return any one of these with probability 1/5. So it's probability 1/5 that I return what's in 3, probability 1/5 that I return what's in 2, etc. Okay, so that's our problem, returning a random element from a linked list. We'll explain this in a minute, but, and as a tool, we have a function called random. So random I takes a value I and returns a number from 1 to I, uniformly at random, and each call to this function is independent of the previous or future calls. All right, so we're going to use this independence. This is the primary vehicle for how we do it, is this random function. So we're going to be analyzing, basically, when do we call it and what values do we supply when we call it. Since they're mutually independent, of course, we're going to determine the probability using the, by multiplying all of the individual probabilities out. But yeah, so that is the problem. We're going to look at a couple different scenarios, but any questions before we get started? Okay. Wow, what happened? Is that that might have been me. All right. Well, okay. So the linked list is I did some last minute editing. I must have accidentally replaced my photo with something. I don't know. Okay. All right. So scenario 1 in choosing a random element from our linked list is that we know n. If we know n, then there is a simple solution. I might have to draw in my linked list a little bit, but yeah, what do? I simply, so n is the size of my linked list. I just take a random number from 1 to n, and that is I, and then I walk through the linked list and I just count how many items I've seen. When I get to location I, if you can imagine, there's a list here. Right, so let's say it's location 3, I count that I've seen 3 items, I return that item. Okay, so I've randomly chosen an element from my linked list, because I knew n beforehand. All right, so simple enough. No problems there. All right, oh, we're back. Good. All right, scenario 2 is that we don't know the length of the linked list, but we're allowed to traverse it more than once. So, well, the solution is pretty simple. I start at the head, I walk all the way through until I get to the end. I count how many elements I've seen, right? Once I get to nil, I know I'm done. And once I've walked through once, I know the value for n, and then I can just run the previous algorithm. So I walk through, I count the items, and then I choose one at random, and then I walk through again until I'm at that location, I return that element. So neither of those are any problem. This requires 2 traversals, which, not ideal, but still doable. But let's say scenario 3, we don't know the value for n. We can traverse it only once, right? So it's a bit stream. It's just some stream of information coming. We don't have enough memory to store everything. So we see something, we have enough memory to store one thing. So we see the next byte that comes through. We decide if we want to store that in our temporary storage. Whether we store it or not, we throw it away, and then we get the next byte, and then the next byte. Okay, so this is not an unusual scenario. This can, there's a lot of low memory applications that do similar things. So in this case, we can assume n is equal to 5, but we don't know this beforehand. We're going to go through the bit stream once and once only. Because the list is on fire and there's ninjas chasing you. So yeah, we go through once and we have to choose one of the items uniformly at random. And by that we mean, of course, with probability 1/5. Okay. And it could be any node with equal probabilities, but we don't know the size. All right, so let's look at the algorithm for that. Yes, all right, so yes, the fire and the ninja are chasing you through the linked list. So return random node, here's the algorithm. We start at, so U is our current node. It starts at the head. I counts how many nodes we've seen so far. We start at 1, and then while U is not equal to nil, right? So, initially U is here, and then it's here, and then it's here, then it's here. Eventually we drop off the end of the list, at which point we, should have chosen something uniformly at random. So while U is not equal to nil, I choose an integer R, which is a random number between 1 and I. And then if that value is equal to 1, then I store what's at my current node, right? So I have that one piece of memory to store something. If R returns 1, I throw away what I saw before and I store the new thing. All right, and that is with probability, well, I is the current location. So if I'm at location 3, it's with probability 1/3. Right? If I get 1 out of these 3, then I throw away what I had before and I grab whatever value's there. Okay. And then I move on to the next node. So this is the successor function, right? So this is how I get, if I'm at node U, here I call successor, it returns the next node, right? So that's all this is this is advancing the pointer. And I also increment my I to say that I see the next item, right? Okay, and then at the end, once U is equal to nil, I'm at the end of the list. I just take the last thing that I remember and I return it. Okay, all right. Questions on this algorithm so far? We're going to go over it in more detail, but okay, so let's say we're at element I. R is equal to a random number from 1 to I. And with the probability that R is equal to 1 is, of course, then 1 over I, right? And if R is equal to 1, then we're going to throw away our old item and grab the new one and remember that one instead, right? And yeah, each of these calls to random is mutually independent, and the probability that we flip our item is 1 over I. Okay. Perfect. Okay, so let's look at what happens on a typical walkthrough. So we start at location 1. In our first pass, I is equal to 1. We say R is equal to a random number from 1 to 1. This, of course, returns 1. So if R is equal to 1, we store that element. So if we have A at location 1, then we store A in our temporary variable X, right? So we always grab the first item, right? Because R in the first pass is always equal to 1. Then we advance to location 2, and we increment our I. At location 2, we have I equal to 2. If R equals 1, we swap. And if R equals 2, then we keep the old value, which is A, which we always have, right? And then in loop number 3, if R is equal to 1, then again, we grab the current one, we throw away the old one. If R is equal to 2 or 3, then X doesn't change. Okay, so I think you guys get the picture. Let's look at some probabilities. In the first step, of course, we select the head with probability 1. In the second step, we select whatever's in location 2 with probability 1/2. In the third step, we select whichever at location 3 with probability 1/3. And like conversely to that, this is the probability that we swap. This is the probability that we don't swap. In location 3, the probability that we swap is 1/3. The probability that we don't swap is 2/3, etc. I think, yeah. So we lay it all out here. At each location, it gets progressively more and more unlikely that I'll grab that element. So yeah, 1/2, probably 1/3, 1/4, 1/5, and no change is 1/2, 2/3, 3/4, 4/5, and so on. Okay. So we know, we know when we swap, we know when we don't. So let's figure out what's the probability that we return some arbitrary element. Okay. So yes. So we're going to choose an arbitrary node V at location K and figure out the probability that we return this node V, or whatever the value is there. So yeah, we want to show that the probability that we return V is equal to 1 over N, even though we don't know N initially. At the end, we know N, so we can verify, but at the time, we did not know N. So event A is that our algorithm returns V, and event AI is the event that X changes during iteration I. So, right, so AK is that X changes at K, for example. All right, and we know the probability of that, of course. The probability of any of these elements being chosen when we're at that location is 1 over I. Okay. So we'll express A in terms of AI, right? So what do we need to have happen in order to return the element at K? Well, if we returned V, then we had to have remembered it when we passed by there, right? So in that step, at location K, we had R equal to 1 with probability 1 over K. In other words, we'll come back to that. But so when I get here, I remember this. Do I really care what happened before that? Or does it have any impact on the outcome? Yeah. So whether or not I remembered any of these previous elements is irrelevant. I could have swapped at every single location or none of them except for the first one. It doesn't matter as long as I replace it when I get to location K. So location K, I choose to swap V, and that is done with probability 1 over K. The other events that I need to have happen, so I need a K to have had, sorry, I need a K to have happened. Yeah, I really stumbled over that. Okay, so once I remember this, I have to keep it until the end. So I'm going to walk through the rest of the list until I get to the end, and I'm not going to select any of those items. Right, so in step K plus 1, it must be that X does not change values. In K plus 2, it must be that X does not change, and so on and so forth, right, all the way to the end. All right, so now my event A, which is that I return element K, is AK and not AK plus 1 and not AK plus 2, and all the way to not AK or AN. Okay, so now we have the intersection of some events. These events are mutually independent because they're based on this call to random. So now I just have to determine the probabilities and show that it's equal to 1 over n. Okay, so the probability of A is equal to the product of all of these individual probabilities. We know the first one is 1 over K. So let's determine the probability of these ones. We've sort of seen them already, but let's do them officially. The probability of AK plus 1 not happening is 1 minus the probability that it does happen, which is 1 minus 1 over K plus 1. And yeah, if I replace this 1 with K plus 1 over K plus 1, then I have a common denominator, and I have K plus 1 minus 1 on top. So I have K over K plus 1. Right, and that's what we saw earlier with the 2/3, 3/4, 4/5, right? That is just K over K plus 1. For K plus 2, we can go through the same set of steps. Again, we have 1 minus 1 over K plus 2. Well, this 1, if we give it a common denominator, it's K plus 2 over K plus 2. Minus 1, we get K plus 1 over K plus 2. And so on. K plus 3, we can do the same thing, and we get K plus 2 over K plus 3. So these are the probabilities of these events. And finally, the last one, not AN, is 1 minus 1 over N. N over N minus 1 over N, which is N minus 1 over N. Okay, questions on that? All right, we're almost at the end. So I take the product of these, and I have this nice little, this product of these probabilities. And the nice thing is that, well, this K cancels out with this K. This K plus 1 cancels out with this K plus 1. This K plus 2 cancels out with a K plus 2 over here. There's an N minus 2 here that cancels out, and this N minus 1 cancels out, and I end up with 1 over N. Right, so all of the intermediate stuff just cancels out, and regardless of my value for N, the probability of returning that individual element is 1 over N. Okay, so that's the algorithm. This style of analysis is, you'll see, and this is also, somebody asked me in the last class, yeah, is this one of these algorithms that never gets used? And it's like, well, sure, this one in particular, but there are algorithms based on this, right? Because there are situations where you see infinite bit streams coming at you. You cannot store them all. You just look at them once, and then you decide whether or not you want to take this element and store it. So there are applications, not exactly this, but very, very similar. Okay. All right, so that's the end of that. I don't think long runs and random bit strings, I see you guys are benefiting from the last class. I showed that to the last class and it was not good, too complicated for the last thing to look at, but so we'll skip it. It's maybe I'll explain it briefly to you, but we won't get into any of the details, right? So do I want to go here? How much time do we got? Yeah, so basically I'll explain the problem just so that you're aware of it. We won't get into any detail. I'll briefly explain a high level version of the solution. This again takes advantage of this mutually independent, right? So if I have a random bit string of length n, essentially how I, find this random bit string is I flip a fair coin n times. All these flips are mutually independent. If it comes up heads, I write a 0, and if it comes up tails, I write a 1. Okay, so we're going to use the mutual independence of this coin flip to figure out the probability that I get a long run in this bit string. And what is a long run? Well, a run is a sequence of bits that have all of the same value. Right, so here I have a run of length 5 of ones. And here I have a run of length 6 of zeros. So I made these randomly, but I happen to get a run of similar bits. So then this question is, should we expect to find a long run in a random bit string, or does the fact that it's random preclude there being long runs? And it turns out that if we say that long is log n bits, or roughly log n bits, then yes, you should find a long run. And in fact, the probability is about 1 minus 1 over n squared. As n gets larger and larger, this 1 over n squared approaches 0. So on a very long bit string, you should really expect to see a long run, or long being log n. You should be very surprised if you don't see it. Okay, so that's the problem. I'll give you the high level solution just so you're aware. Again, it's so at a high level, it's simple. Computing it gets a little more involved than I would like. So yeah, event A, we're just going to choose a value k, and we're going to see the probability that this event contains a run of length k. So yeah, what we're going to find is a lower bound. And we're going to define these events. AI is that there's a run of length k starting at location I. Okay, so I can take on the values from 1 to n minus k plus 1, because if it's a run of length k, then, if this is k items, then the last run of length k could start only there. It can't start anywhere to the right of that. Okay, so then, yeah, if k equaled 5, then A3 occurs, right? So this is a run of length 5. If k is equal to 4, then A3 and A4 both occur. Okay, so now the problem that we're going to run into here is that are A3 and A4 independent? So the coin flips are all independent, but these events now are k coin flips in a row. Right, so probability of A3 given A4, let's say that k is equal to 4 in this case. Is that equal to the probability of A3? If k is equal to 4, what's the probability of A3 just by itself? Let's see if we can we'll just brainstorm the simpler parts of this problem. So A3 is that there's a run of length 4 at location 3. Each of these was determined with probability, right? Each bit was determined to be 1 with probability 1/2 and 0 with probability 1/2. So what's the probability of A3 having a run of 4 ones, let's say? Okay, so the coin flips are independent. So this is A3 is in some sense the probability that I have heads, 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 heads out of the 4 coin flips starting at A3 or location 3. See, I think I lost you already. This is maybe too complicated for the end of a class. Yep. Yeah, it is. It's 2 to the power 4. Sorry, 1/2 to the power 4, right? Yeah. Or did you say 1/2 to the power 4? Yes. Okay. So yeah, it's 1/2 to the power 4. So each of these events I can compute, but now what's the probability of A3 given that A4, assuming in this case that a run is only a run of ones, all right? Well, this is actually only half of the probability, right? Because then I have to add what if they're zeros, but we'll keep it simple for now. What if I know that A4 has occurred? Then what is the probability of A3? So A4 means that I know these are ones. So now what is the probability that I have a run of length 4 starting at A3, given that I already know that locations 2, 3, and 4 are ones? Yeah. Yeah. Exactly. So if I know that these are ones, then I only care if this is a 1. Right? So these are, even though these are composed of independent events, these events are not independent. Because if I know A4 happened, that gives me information about the probability of A3. It changes the probability of A3. So these are not independent events. All right, does that make sense? Questions? Okay, so the solution is, of course, to turn them into independent events. So yeah, let's, I'm going to skip a lot of stuff. I think I have to, this is, there's some nice simple ideas in this problem, but I think overall it's a little too complicated. But what I'm basically going to do is I can't, those events are not independent, but if I look at events, if I divide my bit string into blocks of length k, and then I just look at the individual blocks. So B1 is run of length k in block 1. Well, now this does not overlap with B2, right? If this is block 2, these are, disjoint parts of the bit string, which means they have no coin flips in common, which means they're going to be independent events now. So yeah, we do this a lot in math and probability. If the thing we're trying to compute is too hard, and you could try the complement rule and things like that, they help. But in this case, this problem is simply too hard. So we are going to take something we know how to solve and solve that. So we can look at, B1 intersect B2, intersect B3, and those are independent events, and then we can apply our probability. But yeah, I think I'm going to drop this example from the slides. Does not go over well after everything we just talked about. So that's as far as I'm going to take this one, but yeah. Any questions? See, the other class had to suffer through the whole thing. Yeah. All right. So let's take a look at some simpler examples. Let's see. Okay. So we got 15 minutes left. All right. So here's an interesting one. This is, again, this is simple. This is just conditional probability, and then we'll go to independent. There's another short, not this one. Or maybe it was that one. This one, yeah. So we'll do this one first, and then we'll come back to the previous one. So this is just a nice little example of, and it's interesting. So according to Statistics Canada, a random person in Canada has a probability of 4/5 to live to be at least 70 years old, and a probability of 1/2 to be at least 80 years old. Okay, so these are, probably pretty close to the real thing. So I choose a random person in Canada who turned 70. Now, what is the probability that they make it to 80? All right, so this is conditional probability. So any random person just born has probability 1/2 to make it to 80. But what about John, who's 70 years old? So, this is, we'll say A is 70 years old, or at least 70. So A is the event that they're 70 years old, and B is the event that they're 80 years old. And we know the probability of both of these. Probability of A is 4/5, and the probability of B is 1/2. And now we want the probability of B given A. All right, so I tell you that John turned 70. What's the probability that he makes it to 80? I simply use the A intersect B over the probability of A. Okay, so that's my definition of conditional probability. In this case, though, what is A intersect B? What's the probability of that? So this is the probability that John lives to be 70 and John lives to be 80. Yeah.
What is it before this or times?
Not quite. So if we look at, if somebody makes it to be 80 years old, what do we know about them? Yeah. Yeah. Yeah, anybody who made 80 is also made 70, right? So what does that mean? That means that, well, A is 70 years old, so A is a subset of B. Actually, probably something like this. Okay, so A is a subset of B, so then the intersection of A and B, so if I draw this in a Venn diagram, I have a set B and I have a set A. Now let's put B here. So B intersect A is what? Yeah, it's simply A, right? B intersect A is just A, so this is simply the probability of A intersect B is the probability of, did I write this wrong? Sorry. I wrote them backwards, sorry. Probability, this should be B is a subset of A. Is that right? Well, this is probability of B over the probability of A. However I did it before, I don't know, but yeah. So we can reduce this down to that, well, the probability that they live to 70 and that they live to 80 is just the probability that they live to 80. Right, and that's over the probability that they live to 70. So this is simply 1/2 over 4/5. Invert and multiply, so this is 1/2 times 5 over 4, and that is what, 5/8. Okay, so anybody just born has a probability 1/2 of making it to 80. If you live to be 70, though, your odds have gone up. Right? If you make it to 70, you're more likely to make it to 80 than the average Canadian. All right, so that's a little, I thought, an interesting example of conditional probability, but questions? Okay. 10 minutes. All right, so let's do, here is independence we're going to use again. So Eliza and Nick go and play some darts. They each throw a single dart at the dartboard, and they hit the dartboard with probability, well, Eliza hits the dartboard with probability P, and Nick hits the dartboard with probability Q, And both P and Q are, of course, between 0 and 1. So they each throw one dart independent of the other. And then we have two events. Event E is Eliza's dart hits the dartboard. And N is that Nick's dart hits the dartboard. So we have probability of E is equal to P, and the probability of N is equal to Q. Okay, so sorry, I was just thinking of I just suddenly remembered the other example I was going to show you, but we'll maybe come back to that another time or not at all. So determine the probability that Eliza hits the dartboard, given that Eliza or Nick has hit the dartboard, and the probability that Eliza and Nick hit the dartboard, given that Eliza or Nick hit the dartboard. And since these are independent, we're going to take some shortcuts, right? So we're going to, so let's write out, well, probability of E given E union N is equal to the probability of E intersect E union N over the probability of E union N. Okay, so the first thing we're going to do is simplify our life with a little bit of set operations, right? So what is E intersect E union N? So I have E and I have N. So E union N is everything that's in both of them. And then I intersect that with E, what do I get? Yeah, just E. So the intersection of these two is simply E. So this is equal to the probability of E over the probability of E union N. Okay, while we know the probability of E is P, what's E union N now? All right, so unions and unions and independence don't always work so well. So we're going to, well, we can convert it into these independent events by, of course, inclusion, exclusion. So this is equal to the probability of E plus the probability of N minus the probability of E intersect N. Okay, so yeah, union poses a problem in some sense, but now I have this written in terms of intersections and individual probabilities. I know these two, so this is P plus Q minus, and what is this then? So this is, I mean, we've been writing it like this. These are independent events. So E intersect N is, well, P times Q, yeah. So P times Q, right? This is equal to the probability of E times the probability of N. So yeah, a few set operations and independence have made our life somewhat easier. Oops. So this is equal to P over P plus Q minus PQ. All right, which is not, the nicest result, but it was, if we, make our lives a little bit simpler by using independence and by a few set operations, it's easy to compute. All right, questions? Okay. Let's try the other. We got 5 minutes. So E intersect N given E union N. Let's all right, so probability of E intersect n, which we know, but given E union n, that is equal to the probability of E intersect n intersect E union n, and that is over the probability of E union n. So now this is looking pretty ugly, but maybe we can simplify it. So let's look at the Venn diagram again. I have E, I have N, I have E union N, which is both of them put together. I have E intersect N, which is just this part. So what is E intersect N intersect E union N? Yeah, so it's just E intersect N, right? So I take the intersection of this with all of this, and I just get this back. So this is just the probability of E intersect N. How did we come up with the equation for, I'll come back to that in a second, over the probability of E union N. And these are all values that we know. E intersect N is PQ, and this is P plus Q minus PQ. All right, so a few set operations and independence can make our life a lot easier. Okay, so the question was, how did we come up with this formula for this, right? So how did we get from this guy to this guy? So I just use my definition of conditional probability. So if I have probability of A given B is equal to probability of A intersect B over the probability of B. All right, so now instead of B though, I'm just taking this entire thing and I'm plugging it in where the B goes. Right, so E becomes my A over here, and this entire thing becomes my B. So it's just A intersect B, which is just E intersect E union N over the probability E union N. All right. Oh my God, that's hilarious. My camera's been on this entire time. So the video might have a picture of the ceiling on it. I don't know. All right. Any questions? Okay. So I think we'll leave off there for today. So yeah, keep working on your assignment 3. It's due next week, next Sunday, and yeah, have a good weekend, and I'll see you guys next week.